In this lesson, we are going to talk about derivatives and how they can help us determine the shape of a graph. Now, previously in the section where we talked about local maxes and mins, I kind of hinted at this theorem called the first derivative test, and we kind of talked about it without me directly naming it. So this will hopefully be a little bit of a review. But the first derivative test tells us that if a function is continuous on an interval I, and you have a critical point C, right, then you can check test points to see if it's a local max or min. So if the derivative changes sign from positive to negative, then you have a local maximum. The second part says if the derivative changes from negative to positive, then we have a local minimum. And if the derivative has the same sign, then it's neither a local max or a local min. So let's look at this first example. We have the graph of the function x to the third minus 3x squared minus 9x minus 1. So we want to take the derivative and find the critical values. That's the first step. So when I take the derivative, I'm going to get 3x squared minus 6x minus 9. And to find the critical points, I'm looking to see what values of x make the derivative either 0 or undefined. And in this case, there are no values of x that would make the derivative undefined, but we can find values that would make it 0. I can factor out a 3 and divide both sides by 3. So that would give me x squared minus 2x minus 3. And then I can factor this as x minus 3, x plus 1. So my critical points are 3 and negative 1. So now what we're going to do is we're going to make a sign chart. So I have negative 1 and 3, and we put our critical values on the sign chart. Now, we pick test points. Now, if I pick a test point on the first interval, so from minus infinity up to negative 1, let's say I pick the test point x is negative 2. When I plug negative 2 into the derivative, I'm going to find that I have a positive slope at that point. So that means that f is increasing on this interval. Now, between negative 1 and 3, let's say I pick the test point 0. If I plug in 0, I'm going to get a negative value, which means my slope is going to be negative. And so my function is decreasing on the interval between negative 1 and 3. And then if I pick something bigger than 3 on the interval from 3 to infinity, let's say I pick the value x is equal to 4 as a test point. When I plug 4 into the derivative, I'm going to get a positive value, which means the function is increasing. Now, because on the interval from minus infinity up to 1, the graph is increasing, and then from negative 1 to 3, it's decreasing. Based on that first derivative test, that tells me that x is equal to negative 1 on the graph is a maximum point. Then from 3 to infinity, it's increasing again. So because it's decreasing and then increasing, that tells me x equals 3 is a minimum. So when we graph this on our calculator, so let's let increasing intervals be yellow, because I like to color code, and let's let decreasing intervals be purple. So if you look from minus infinity up to x equals 1, this is increasing. I'm going up left to right. Then I have a maximum at x is equal to negative 1. Then from negative 1 to 3, this interval is decreasing, and then I have a minimum at x is equal to 3. Then from 3 to infinity, again, I'm increasing, and then we're done checking. So if I were to check this like a spot check, I know that my derivative at any point on the interval from minus infinity to negative 1 is positive, because if I pick a point to check, the slope of that tangent line is positive. If I pick a point on this interval, the slope of the tangent line at that point is negative. And then if I pick a point on this interval from 3 to infinity, the slope of that tangent line is positive. So where the tangent lines are positive and negative indicate where the function is increasing and decreasing. So we have another example here that we can use the first derivative test to find all the local maxes and mins. And our function is 5x to the 1/3 minus x to the 5/3. And then we can check it with a graph. So first we'll take the derivative. So when I take the derivative, I'm going to get 5/3 x to the negative 2/3 minus 5/3 x to the 2/3. I can simplify this by making that negative 2/3 exponent positive by taking the reciprocal. So then I would have 5 over 3x to the 2/3. Then I would subtract 5/3 x to the 2/3. And then I can find a common denominator and combine the two fractions together. And finally, I would end up with 5 minus 5x to the 4/3 over 3x to the 2/3. Then we have to set the derivative equal to 0 to find the critical values and figure out also where the derivative is undefined. Now, because the derivative is a fraction, we can see that it's undefined at x equals 0. When we set the numerator equal to 0 to find where the derivative is 0, we get that x is plus or minus 1. So our critical values are x is 0, and where the function is 0, we have x is equal to plus or minus 1. So these are what we're going to put on our sign chart. So I have -1, 0, and +1. So we have to now check these intervals. So my test points, let's say I pick -2, -1/2 for that interval. Let's use +1/2 for this interval. And let's let x equal 2 be the test point for that last interval. Now, when I plug in my test points to my derivative, I'm going to get that the function is decreasing on the interval from minus infinity to -1 because the derivative is negative on that interval. I'm also going to get that it's decreasing on this interval here from 1 to infinity, because when I plug in 2 into the derivative, I'm going to get a negative value. And so that tells me that the derivative is negative, which means the function is decreasing on that interval. Now, when I plug in points for x equals -1/2 and x equals 1/2 into the derivative, I'm going to get that the tangent lines on that interval are positive, which means the function is increasing. So on the first interval, it's decreasing, and then it's increasing, which tells me that this is a minimum. So x equals -1 is a minimum because it decreases and then it increases. Now, there's no sign change from the interval from -1 to 0 to the interval 0 to 1. So this is not a local max or min. Now, the next two intervals, if I check from 0 to 1, it increases, and then from 1 to infinity, it decreases. So at x equals 1, this is going to be a local max. Now, if we check that on our graph, we can see that on this interval here, from minus infinity up to 1, we're decreasing. Then we have that critical value at x equals -1, and because it changed signs on the derivative from negative to positive, we said that that was a minimum. And you can see on the graph that that's true. Then from -1 to 0, it's increasing, and then from 0 to 1, it's increasing. And you can see that this point right here at 0 is not a local max or min, which is why it doesn't have a sign change on the derivative. And then lastly, from the point x equals 1 to infinity, that's decreasing. So that point we found was a local max because it goes from increasing to decreasing. So now we're going to talk about concavity and points of inflection. If we say that a graph is concave down on an interval, that means it's going to have a shape that looks like a frown. If we have a graph on an interval that is concave up, and it looks like a smiley face, that's called concave up. Now, the way that we can tell using derivatives whether the function is concave up or concave down on an interval is based on the second derivative. If the second derivative is negative, meaning less than 0, then it's going to be concave down. If the second derivative is positive, then it's going to be concave up. When the second derivative is equal to 0, that's where you're going to have a point of inflection. And that's the point in which a graph turns from concave up to concave down. So here's an example. So if you look up here in the box, I'll draw you a picture. Here's a graph that looks like a cubic. I'll use green for concave down, and I'll use pink for concave up. The graph is concave down on this interval, and the graph is concave up on this interval. The point of inflection is the point where it changes from concave down to concave up, or vice versa. So a point of inflection would be right here. Now, this graph here that I got from the book does a really good job of showing the difference between the first derivative and the second derivative. Now, if you look on the interval, I'm tracing here in green, from here to here in green, that's concave up. So if you notice on these two intervals here, the second derivative is positive. Now, here's our inflection point, and this is where the graph is concave down. So my second derivative on this interval is negative. Now, let me erase and let's look at the first derivative. Now remember, the derivative is negative when the graph is decreasing. So if I trace left to right using my green, this here is decreasing. And then this here is decreasing because I'm tracing it left to right and going down. So the first derivative is less than 0, meaning negative, on that interval, and the first derivative is negative on that last interval where I have it highlighted green where it's decreasing. Now the first derivative should be positive when the graph is increasing, which is from here to here in pink. So my first derivative is positive on that pink interval, and then the second pink interval here, my first derivative is positive. So let's do this example where it shows how to check for concavity. So we first need to take the derivative, so f prime of x And f of x is x to the third minus 6x squared plus 9x plus 30. So when we take the derivative, we're going to get 3x squared minus 12x plus 9. Then we have to take the second derivative if we want to check to see where it's concave up or concave down. So I'm going to take the second derivative, so that's going to give me 6x minus 12. Now, if I set the second derivative equal to 0, that's going to give me that x is 2. So this is going to be my point of inflection. I'm going to abbreviate it POI, point of inflection. So that's where it's going to change from either concave up to concave down or from concave down to concave up. So we're going to do this and check by setting up a sign chart. So I put my point of inflection on there. That's where my derivative is 0. And then I pick test points just like before. But now instead of plugging it into the first derivative to see where it's increasing and decreasing, we plug our test points into the second derivative to see where it's concave up and concave down. So let's say I pick x is 0 for the interval from minus infinity to 2. And let's say I pick the test point x is equal to 5 for the test point on the interval from 2 to infinity. Now, if I plug in 0 into the second derivative, I'm going to get a second derivative that is negative, which tells me that we're concave down on that interval. Now, when I plug in my test point of 5 into the second derivative, I'm going to get a positive value, which means my concavity is up on that interval. So when I check that against my graph, here's my point of inflection. I'm concave up when I'm greater than 2, and I'm concave down when I'm less than 2. So that definitely works, and I already have the graph because I copied it from the textbook, but you can certainly put this in on your calculator. Now let's talk about the second derivative test. The first derivative test helps us determine where there's local maxes and mins by looking to see where the function is increasing and decreasing. The second derivative test also helps us find where there's local maxes and mins based on the concavity of the function on an interval. If you have a value of c that makes the first derivative equal to 0, then when you check it on the second derivative and it's concave up, if you have a point that has a tangent line of 0 on an interval that's concave up, then that has to be a minimum. If you check that value of c that has a tangent line that's 0 at that point on the graph, and the second derivative tells you that you're on an interval that's concave down, then that point has to be a maximum. And then if you plug in that value of c and the second derivative tells you that it's still 0, then the test is considered inconclusive. Let's use, in this example, the second derivative test to see where the local maxes and mins are. So we have this function, x to the fifth minus 5x to the third. So I'm going to take the first derivative, which is 5x to the fourth minus 15x squared. And I want to find my critical values by looking to see where the values of x occur that make the derivative 0 or undefined. Now, there's no values of x for the derivative that would make it undefined, but we do have values of x that would make it 0. And so if I set the derivative equal to 0, and I solve that equation, I'm going to solve it by factoring. So I'm going to pull out a 5x squared. And that's going to leave me with x squared minus 3 on the inside. And then, so I'm going to set each of those equations equal to 0. And what I'm going to get is that my critical values are 0 and then plus or minus the square root of 3. Now I have to take the second derivative and plug in those critical values and check to see if they lie on intervals that are concave up or concave down. So when I take the second derivative, I'm going to get 20x to the third minus 30x. So now I'm going to plug in for the second derivative, I'm going to plug in 0. If I plug 0 into the second derivative to see if it's on an interval that's concave up or concave down, I get that the second derivative of 0 is 0. So this tells me that it's inconclusive. I don't know anything about that point yet. When I plug in positive square root of 3 into the second derivative, I'm going to get a positive value, which means on that interval, it's concave up, which means if it's concave up, then at x equals the square root of 3, it has to be a local min. Now, if I plug in negative square root of 3, I'm going to get a negative number, which tells me on the second derivative at x equals negative square root of 3, that interval is concave down, which means if it's concave down, then that point at x equals negative square root of 3, that's a local max. Now, by the second derivative test, we can conclude that f has a local maximum at negative square root of 3, f has a local minimum at x equals positive square root of 3, and then we have a critical value at x equals 0, but based on the second derivative test, we weren't able to tell what's going on at that point. But when we look at that graph, we can see that x equals 0 is actually an inflection point. So on this interval here, before we get to 0 is concave up, and then after 0 is concave down. So x equals 0 is a critical point, and it's an inflection point. And then at negative square root of 3, we have a local max, and then we said at positive square root of 3, we have a local min. So overall, on this last page of the notes, we see a really neat graph that shows you all different features of the graph. So if I trace this left to right, this interval right here in pink is increasing. So the first derivative is positive because all the tangent lines on that interval is going to have a positive slope. Now, when we get to this point right here, we have a cusp, which means the derivative at that point A is undefined. It's not differentiable at that point A. Then, if we keep going, we have on this interval, we have that the graph is decreasing, so the derivative is negative. At this point right here, we have a horizontal tangent line. So the derivative at that point, b, is 0. And it goes through all these neat features of the graph. So let me keep going here. So on this interval here, we're increasing, which means the derivative is positive. Then we're still increasing here to here, so the derivative is still positive. But we have a horizontal tangent line at that point. So at x equals c, we have a derivative that is 0. Then we have an interval that is decreasing, and we have a maximum, a local maximum here where we have a horizontal tangent line at that point d. So the derivative of that point, d, is 0. Now remember, additionally, don't forget, when the graph looks like an upside down bowl or a frown shape, that's where the second derivative is negative. And when the graph has an upright bowl shape or a smile shape, that's concave up, and the second derivative will be greater than 0. And where the second derivative is equal to 0, that's a point of inflection.